Earlier this week we discussed the most common form of hydropower. There are, however, more ways to harvest energy from water. In this video we'll take a look at tidal energy. Tidal energy is a special type of energy since just like geothermal energy, solar radiation is not the primary energy source. The tides are caused by the gravitational pull of the moon and the sun. At high tide, the water has a greater height than at low tide. This height difference means that some potential energy is available. Just as in a hydropower plant, the potential energy is transformed into kinetic energy, which is then used to generate electricity. The main difference is that the water reservoir gets replenished with the tides instead of through rainfall. Alternatively, tidal energy can be harvested by placing turbines in a tidal flow in the sea. This will be explained in the next video. The primary energy potential is calculated in the same way as with hydropower. The potential energy is equal to the mass of the water multiplied by the gravitational constant multiplied by the height difference. If we look at this equation more closely, we see that the mass depends on the height difference between the low and high tide. Therefore, in total, the potential energy depends quadratically on this height difference. The main conversion losses are also the same as those of a hydropower plant. As you may remember, these were caused by the friction, turbine and electrical losses. The energy yield is determined by the tidal variations, which depend on the position of the sun and the moon with respect to the earth. From these two, the influence of the moon is the greatest. This is because the moon is closer to the earth. These pictures show the differences between the spring and neap tides. The orange sphere represents the tide created by the sun and the blue sphere represents the tide created by the moon. The highest tides are created during spring tides. This is because the moon and the sun are aligned with each other. About 7 days later, during neap tide, the sun's pull is perpendicular with respect to that of the moon. This creates lower tides. However, it's still important to ask yourself the question, what is the real source for tidal energy? You might think it's the interplay of the gravitational potential between sun, moon and the ocean water on planet Earth. But does the gravitational force between the moon and Earth weaken due to the consumption of tidal energy? No, it does not. For a large part, the energy source is the kinetic rotational energy of planet Earth itself. The tidal friction gradually slows down the rotation of planet Earth. Every 100 years, the days are getting 2.3 milliseconds longer. Let's run through a calculation example to assess the potential of tidal energy. Let's assume a height difference of 10 meters between low tide and high tide flowing through a column with a surface area of 1 square meter. The density of salt water is approximately 1025 kilograms per cubic meter and the gravitational constant is equal to 9.81 meter per square second. With this data, we can calculate the energy potential, which is approximately equal to 1 megajoule or 0.27 kilowatt hour per time. Because this is for an area of 1 square meter, this is actually the potential energy density for this basin per square meter. So what about the power density? As there are 2 tides in a day, we can say that the source gets replenished twice a day. Therefore, we have 2 megajoules or 0.55 kilowatt hours per square meter per day. If we divide this by the total hours in a day, we find that the average potential power density is roughly 23 watts per square meters. Note that the system efficiencies have not yet been taken into account. For our next example calculation, we will do something different. We will calculate the capacity factor, but also using this information, find out the system's efficiencies. To do this, we will take a look at the Reims tidal power station in France. This tidal power station is one of the biggest tidal power stations in the world with an installed capacity of 240 megawatts. It produces on average approximately 500 gigawatt hours per year. The height difference is 8 meters and the area of the reservoir is 22.5 square kilometers. First, we will calculate the capacity factor by dividing the annual energy yield by the nominal capacity times the number of hours in a year. This results in a capacity factor of 0.24. The average output power density of the plant is the installed capacity of 240 megawatt multiplied by the capacity factor of 0.24 divided by the surface area of 22.5 square kilometers. Doing this, we find an average power density of 2.6 watts per square meters. Before we can calculate the system's efficiency, we first have to calculate the primary energy potential of this station. With a height difference of 8 meters, we obtain a potential energy of 0.63 megajoules per area per tide. This is a total of 0.35 kilowatt hours per square meters, which equates to an average power density of 14.6 watt per square meters. We can now find the system's efficiency by dividing average output density by the average primary power density. This equals to 18%. A big advantage of tidal energy is that tidal plants have a very long lifetime. The Rens tidal plant, for example, has been running since 1966. Despite tides being very predictable, power generation is not continuous. During 2 quarters of the day between low and high tide, the basin is filled and no power is generated. Finally, the same boundary conditions apply as for other hydro energy generation. The main condition is that there has to be a location where there is a high tidal fluctuation. This is not very common around the world. In addition, the construction of a tidal plant and reservoir will have a large impact on the surrounding flora and fauna. Only a few tidal plants exist all over the world. They have a combined capacity of around 500 megawatts. This is why the contribution of tidal energy to the world's electricity production can be ignored. According to our previous calculated capacity factor, this results in an annual yield of 1.05 terawatt hours per year. The global yield per person per day equals to a small value of 0.38 watt hours. The power density of tidal energy is between 2.3 and 3.5 watts per square meter. There are not enough locations with a suitable tidal fluctuation to meet the electricity demand of 2040. However, if there would be enough suitable locations, a tidal reservoir of 1.4 megakilometers would be sufficient. A few large-scale projects are still under design in Russia and in the UK. Predictions for the world power potential can exceed 120 gigawatt, which is relatively small in reference to other renewable energy sources discussed this week. Nevertheless, tidal energy is still a very reliable energy technology with a long lifetime.